Aurora, Katya, we have a problem. Our 2-meter ladder is falling down.
We need to get the rate of change right now. Come quickly.
Okay, we're coming. We need to go right away.
Yeah, of course, take the calculator.
Okay guys, first of all, we need to do a research. Alan, tell us what implicit differentiation is and why rates of change are an example of this.
When we find a derivative, you are finding the rate that one thing is changing as another changes. Y is changing on dy and x is changed on dx. When we want to differentiate something of the form f of x elevated to g of x, and the letter when we is impossible to solve for this variable, where y is given in terms of x, we can differentiate an expression in y with respect to x by treating y the same way we should treat g of x and using the chain rule.
Before stating the problem, we must know what are related rates of change. These are an application of differentiation that allows us to find the rate in which one thing is changing as another changes, just like when we find the derivatives. Now, let's mention some characteristics. Number 1. The variables are related in a definite way. Number 2. The values of the variables are given at some particular instant. And number 3, the problems might involve formulas like area or volume and others.
And Jenani, what are we exactly looking for?
The problem of the project is that a 2-meter long ladder rests against a vertical wall. The bottom of the ladder suddenly starts to slide away from the wall at a rate of 0.1 meters over seconds. We need to know how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 0.5 meters away from the wall. First, we drew our diagram and analyzed our data, which is x of t equals 0.5 meters, z of t equals to be defined, and y of t equals to be defined, in order for us to be able to know how fast is the top of the ladder coming down when the bottom of the ladder is 0.5 meters.
Now, since the ladder and the vertical wall make a right triangle, we should use the Pythagorean theorem and apply it to our equation.
Then we're gonna apply implicit differentiation in equation 1. That makes us get 0 equals 2y of t times dy over dt plus 2x of t times dx over dt. So now we're gonna solve for dx over dt. That means we're gonna isolate it to get equation 2. So next we're gonna get the value of y of t in equation 1, since we don't have it. We're gonna plug in the values that we know and solve for the y. Okay, so now it's time to check our data again. We know now that we have y of t, x of t, and z of t. Now we can solve what they're asking for. As the last step, we're gonna substitute the values that we got in equation 2, and we're gonna get that dx over dt is equal to minus 0.3873 meters per second. That means that when the bottom of the ladder is 0.5 meters apart from the vertical wall, that's gonna be the rate of change.
We investigated about related rates, then we analyzed the problem and the variables given. We wrote down the formulas, variables, and equations. Then we made the implicit differentiation, isolated variables, solved the rate of change, and concluded with the importance of related rates.
After investigating about rates of change, searching examples and figuring out how to solve them, we can conclude that this project can help us to understand how rates of change are applied in real-life situations, such as finances, economics, and engineering problems in our situations. There are some examples that are similar to the problem that we solve. Some examples of these are analyzing finances, figuring out how much someone is saving per day, month, and year.